Hello, welcome to lecture 37 of the course. So, in the last lecture we have talked about the Rayleigh-Ridge method, which was a technique to approximately find out the mode shape and natural frequency of a continuous system for cases with complex geometry like varying cross section and varying mass distribution. So, we have seen in the earlier lecture that how to use Rayleigh-Ridge method to obtain an approximate value of the mode shape and natural frequency using some known trial function and by minimizing the Rayleigh's quotient. In this lecture as well, we will be talking about another approximation technique, another technique by which we can obtain the natural frequency and mode shape of a continuous system with complicated geometry. Perhaps this collocation method is much easier to implement than the Rayleigh-Ridge method. So, let me talk about collocation method in details. So, in collocation method, let me start with the equation of motion. So, let me start with the equation of motion of an Euler-Bernoulli beam. Okay. So, let me write down the equation of motion. Now, I assume normal mode of vibration and therefore say that yxt is equal to the mode shape phi x into the time function dt. Now, if we plug this into this equation, we have done this exercise several times before. So, I will skip the steps and we can write this directly as So, this is the equation involving the mode shape. Now, what we have to do is that we have to find an approximate solution for the mode shape. For the cases which had simple geometry like uniform cross section, we need not obtain an approximate value, but for cases where mx and exi are function of x, we cannot solve this in a closed form and get the solution for phi x. So, similar to Rayleigh-Ridge method, here also we assume that phi x is going to be some constant C j into trial function psi j x. So, j equals to 1 to n. So, this psi j x is the trial function and C j are the constants which are not known. So, we have done similar exercise for Rayleigh-Ridge method. Here also we are going to do similar exercise. So, this psi j which are trial functions, these are known. We will assume known functions. And this Cj's which are constants are unknown and as needs to be derived. So now let us start by finding out the Cj. So let me do that. So if I do that, I can say that if I plug in that into this equation, I will have d2 dx square now. So, in Rayleigh-Ridge method we had find out this Cj's by minimizing the Rayleigh's quotient. Here we will adopt a different technique. Now, there are different kinds of collocation method. There is boundary collocation method, there is interior collocation method, there is mixed collocation method, out of which interior collocation method is the most popular one. Interior collocation is most popular and often loosely called as So, often I mean what this means is that often when we say collocation method, we by default mean interior collocation method, though there are other forms of collocation method as well, but the interior collocation method is the most popular one and I will talk about it. So, what happens in interior collocation method is that the trial functions that are psi j's, the psi j's need to satisfy all the boundary conditions. So, they need to satisfy the displacement boundary condition as well as the force boundary condition, or in other words the natural boundary condition and the force boundary condition. So, it should satisfy conditions like displacement is equal to 0, rotation is equal to 0, or shear force is equal to 0, or bending moment is equal to 0. So, a trial function in case of interior collocation method needs to satisfy all the boundary condition, unlike in Rayleigh-Ridge method where the trial function required to satisfy only the force boundary condition or the displacement boundary condition. Okay. So, now what happens? Now, once we choose the trial function which are satisfying all the boundary conditions, what we do now is that we choose station points. Now, what are the station points? Let me call them as SI. What is the station point? Station points are just points on the bar or beam. So, suppose I have a beam with varying cross section, and I can choose any point which is say at x equal to, so say this is x equal to 0 and this is x equal to x1, this is x equal to L. I can choose any points within the domain or on the beam and bar, x equal to x2, x is equal to x3, and this points will be the station points. So, these are all my station points. What is the significance of station points? We will talk about that later. So, just right now let us understand what is station points. Station points are just arbitrary points on the beam or bar that we are trying to analyze. Now, what happens is that in collocation method or interior collocation method, in interior collocation method we say that the equation is getting satisfied at the station points. So, the equation that we had, let me go back to the equation. So, the equation that we had, which was d by dx square EIX psi j sorry for this. Summation of Cj psi j double dash minus omega square mx So, this equation is where I have approximated my phi x with summation Cj psi j x. So, since it is not the exact solution of the equation, since this is an approximate solution, this is approximate phi x, this is not the exact solution. Therefore, this approximation does not make this equation equal to 0. But what we do is that we force that at the station points Si, this is going to become to 0. This is what we are going to enforce. We are going to enforce that at all the station points, this equation which contains Cj and psi j is going to go to 0 at the station points. So, from this enforcement we will find out the constant Cj's which are going to satisfy this criteria. Let me explain this in another word. So, we have this equation. We are saying that this equation is forced to become 0 at the station points. Now, if we need to find out the constant Cj's which is going to make this equation go to 0 at the station points. Therefore, we get a set of equations which will help us to obtain the values of Cj's. Now, the number of trial function should be equal to the number of station points. So, if we have taken 3 trial function, we have to choose 3 station points. So, we will get 3 equation each corresponding to one of the station point, and from this 3 equation we can solve the 3 unknown Cj's, that is C1, C2 and C3, and thereby if we write down the equation, finally it is going to get a matrix form of K minus omega square M is equal to 0, where K is n cross n, M is n cross n, where n is the number of trial functions. Now, what is K? What is Kij? Kij is going to be d2 dx square into Eix psi j double dash x at x equal to Si. Similarly, what is Mij? Mij is going to be mx psi j x at x equal to Si. Now, one thing should be noted is that this matrix K and M, unlike the Rayleigh method, is not symmetric. It is unsymmetric because Kji is not equal to Kij, and Kji is d2 by dx square into Eix psi I double dash x at x equal to Sj. Similarly, Mji is equal to mx psi Ix at x equal to Sj. So, we can see that Kij is not equal to Kji and Mij is not equal to Mji. So, they are not symmetric. So, this is how we are going to solve a problem using collocation method. What I am going to do now is going to solve an example which will help us to clarify the concepts that we have learned. So, let us go back to the equation, to the example that we have solved using Rayleigh method. We will solve the same example using collocation method. So, the problem statement is of this form. So, I have a bar under axial vibration. The bar does not have a uniform cross section and the cross section is non-uniform. At x equal to 0 and x equal to L, okay. The displacement is uxt. The variation is given as Eax is equal to, oh, this is given here, so I need not write it again. So, this is given as this one and mx equal to 1 minus x by L. Now, how are we going to solve this using collocation method? So, it has been mentioned that we have to use 2 trial functions. So, let us now choose the 2 trial functions. So, let me first choose the trial function, that is the first job. So, what would be psi 1 x and what should be psi 2 x? Now, the only criteria that the trial function should satisfy is that the trial functions need to satisfy all the boundary conditions. So, the boundary condition here is that the displacement is 0 at x equal to 0. So, psi 1 0 and psi 2 0 should be equal to 0, and there is no force acting at x equal to L. Therefore, E A x E x A L into psi 1 L dash and E A L into psi 2 dash L should be equal to 0. Now, we have to choose such a trial function which is going to satisfy these two conditions. The one possible trial function, set of trial function is sin pi x by 2L and sin 3 pi x by 2L. We can see that these two trial functions are satisfying the boundary condition, because at x equal to 0, psi 1 0 is equal to 0, and at x equal to L, psi 2 L is equal to 0. Sorry, psi 1 0 is equal to 0, as well as psi 2 0 is equal to 0, and psi 1 dash L is also equal to 0, and psi 2 dash L is equal to 0. Okay. So, therefore, this satisfy all the boundary conditions. So, if these two are trial function, then the mode shape phi x can be written as j equals to 1 to 2 C j psi j x, which in expanded form is C 1 psi 1 x, and I know psi 1 psi 2, I do not know C 1 C 2, which I need to find out. Now, let me see how we can do that. So, if I substitute that into the equation, so the equation for axial bar or bar under axial vibration So, bar under axial vibration, the equation can be written as d dx and that is equals to minus omega square. So, if we substitute phi x is equal to summation of C j psi j x into this equation. So, this therefore become d dx If I expand this, I can write this as d dx of this is what I get at the station points. So, at x equal to Si. This is going to be equal to 0. So, now since there are two trial function, there should be two station points. So, let me choose the station points as S1 is L by 4 and S2 is 3L by 4. So, the choice of the station points are arbitrary. So, we can choose any station point, but should be within the boundary, should not be x equal to 0 or x equal to L, it should be somewhere in between x equal to 0 and x equal to L. So, we could have very well chosen this as S1 equals to L by 2 or S2 equals to L by 4 or whatever. I mean any two distinct station points should be fine. Now, therefore, at the station points these are going to be 0. So, so since there are two station points, for each station point I will get an equation of like this, and therefore, I am going to get two equation, and which can be written as k minus omega square m into C1 C2 is equal to 0. So, this k is 2 cross 2, m is 2 cross 2. Now, our job is to find out what is k11, k12, k21 and k22. Similarly, what is m11 or m12, m21 and m22. Let us try to see what they are going to be. So, what is going to be k11? K11 is d dx into EAX into psi 1 dash x at x equal to L by 4, which is my station point 1. So, if this is k11, I can write this as d dx 2EA and 1 minus x by L, and then I have pi by 2 L cos pi x by 2 L, x is equal to L by 4, which will turn out to be pi EA by L square cos pi by 8 plus 3 pi by 8 into sin pi by 8. This is k11. Similarly, k12 is going to be d dx EAX psi 1 dash x at x equal to 3L by 4, which is my station point 2, and that is equal to, if you look into that, that is going to be equal to 3 pi EA by L cos 3 pi 8 plus, so 3 pi, sorry, this is pi L square, 3 pi 8 plus pi by 8 into sin 3 pi by 8. Similarly, I can find out k21 and k22. Now, what is m11? m11 is going to be mx into psi 1 x at x equal to s1, which is going to be 2m 1 minus x by L into sin pi x by 2L at x equal to L by 4, which is going to be 3 m by 2 into sin pi by 8. So, this way we can find out M12 as well as M21 and as well as M22. So, once the K and M matrix are obtained, we can solve the matrix equation, which is very similar to solving the matrix equation for a multi-degree of freedom system, and we will get approximate values for. So, from once we get K and M matrix, we can solve this equation and we can get approximate value of omega 1 square, omega 2 square, and corresponding to each omega I will get two values of, okay, and thereby we can get an approximate value of the mode shape as well as natural frequency. The best part of collocation method is that it does not involve any integration, unlike the Rayleigh-Ridge method. So, the calculations are much more simpler, and we can even use more number of trial functions and get a better approximate solution for the mode shape and natural frequency. So, with this we will end this lecture. In the next lecture, we are going to talk about energy method or the Euler-Lagrange equation to obtain the equation of motion of a multi-degree of freedom system. So, we will be moving into module 4 with next lecture. Thank you.